Hi, my name is Alan, and I'll be presenting our work titled Spacetime Correspondence as a Contrastive Random Walk. And this is joint work with Andrew Owens and Alexei Efros. The goal of representation learning is to learn to describe data from the environment in a way that's useful for downstream tasks, each of which might require different information. A simple and popular approach for representation learning is modeling pairwise similarity. So for example, given x1 and x2, which are inputs that are known to be similar in some way, the objective is to maximize the similarity of their latent representations under our model. Of course, this is not necessarily a new idea, and yet it's led to a lot of the recent progress in self-supervised representation learning. So what are the keys to this recent success? Well, on one hand, we've definitely gotten better at optimizing Siamese nets, but perhaps more importantly, we've really figured out how to generate a lot of training data by using data augmentation. Data augmentation allows us to generate training data by randomizing things like the cropping, the color, the flipping, or the blurring of an input image. This allows us to simulate variation in things like the context or the lower level appearance of the image in a surprisingly useful way. That said, data augmentation has its drawbacks. For one, it isn't actually unsupervised. There are a lot of hyperparameters that we actually have to tune. Moreover, data augmentation isn't very naturalistic, and there are many different kinds of transformations that they can't possibly emulate. But we tend to forget that the images that we want to learn representations from are really just snapshots of dynamic scenes generated by a pretty good simulator, which is just the real world. There's an abundance of smooth and natural changes in context, appearance, and composition in the dynamics that we actually see captured in video. Dynamics are important because they expose to us the composition of a scene and how it changes. Correspondence across space and time gives us a sense of the instances of the scene and instance-level factors of variation. Common fate, which is just the idea that some parts of the scene will move together while other parts don't move together, is a strong cue for the perceptual organization in the scene. And so together, these cues are important for object-centric learning about the extent of objects and scenes and how they actually might change. Of course, all of this structure and all of this signal is really hidden latent in the data. And the key question is how to harness it without any sort of human supervision. First, there's a long line of work that has sought to learn representations from video. Earlier work mainly focused on leveraging the temporal coherence we see across frames, using techniques like slow feature learning, sparse coding, ICA, and earlier models of autoencoders. More recent work has also considered using contrastive learning or coming up with self-supervised pretext tasks, like, for example, learning to unshuffle a shuffled sequence of frames. More recent work has also sought to directly mine training data from video by using tools like trackers and detectors. These approaches, however, tend to involve complex architectures or require additional supervision in a way that might actually introduce additional bias or hinder their robustness and scalability to large unlabeled video data. So in this work, our main interest is developing a simple end-to-end approach for learning representations for correspondence from unlabeled video. While we'd like to do this without any supervision, let's first consider the case where we do have supervision. So if we do have these labels, then we can just use them to do supervised representation learning, as we said. More interestingly, these labels can provide implicit supervision for the latent views that actually lie in this intermediate frame. So for example, if we try to match these two views through this intermediate frame, we can provide supervision for the unlabeled data that lies in that frame. And moreover, we can consider a distribution over these views, over these correspondences, in a way that allows us to consider different kinds of associations. Finally, we can even get rid of this need for this target by choosing our training sequences in a careful way. So for example, we can turn all of our training sequences into palindromes, which are simply sequences that are identical when reversed. And so for these sequences, we actually know our targets by construction. And so in this way, we can actually turn our supervised learning problem into a self-supervised learning problem, where a single self-supervised target provides supervision for all of these intermediate comparisons in this graph. In this work, we operationalize all of these ideas by casting correspondence as a random walk on a space-time graph. In this graph, the nodes are patches extracted from each frame, and only nodes that are adjacent in time will share an edge. and the strength of this edge will be determined by pairwise similarity in a learned representation. Our aim is to learn the representation so as to maximize the likelihood of reaching a corresponding target, shown in green, when starting from the node shown in blue. As we will see, this formulation allows us to consider in an efficient way and to learn from many different paths going through this graph. Moreover, we can supervise all of these chains of comparisons along these paths with a single target shown in green. Concretely, given some frame at time t, we extract a set of nodes qt. And in practice, we can do this simply by, for example, extracting a grid of patches. We can map each of these nodes to their representation using an encoder. And this encoder will be exactly what we'd like to learn. For a pair of frames, we can compute the transition matrix by first computing the matrix of pairwise similarities between all adjacent nodes. We can then turn this matrix into a stochastic matrix by simply normalizing its rows with the softmax function. And so this will tell us essentially the transition probabilities of our walk on the graph. Given the space-time nature of our graph, we can view the random walk essentially as implementing probabilistic patch tracking across time. Moreover, we can efficiently compute long-range correspondence simply by chaining together these steps on the graph. So under this formulation, learning a representation essentially amounts to fitting the transition probabilities of this walk on the graph. And this is reminiscent of the classic work from Marina Mela and John Boschi titled Learning Segmentation by Random Walks, which is presented at NeurIPS almost 20 years ago. Let's first consider the case of fitting one step on the graph. We can do this by maximizing the probability of transitioning to the correct target node. This amounts to pushing the representation of the query node in blue towards the representation of the target shown in green, or in other words, the positive, and away from the representation of all of the other nodes, or the negatives. And so in this way, we can actually view each step of our walk as a contrastive learning problem. More interestingly, we can consider what happens when we fit the k-step walk. To compute the k-step transition matrix, we simply multiply all the intermediate transition matrices, essentially summing over all the intermediate time steps. So in this way, when we go to fit the k-step transition matrix, we're actually providing supervision for all these intermediate transitions, and therefore providing supervision to all the latent views that we actually use to chain these paths together. So in an easy case where correspondence is obvious, there might not be too much to learn. But in a harder case where there's a bit of ambiguity, this formulation allows us to consider multiple paths through the graph and to learn from multiple paths through the graph, and therefore to backpropagate across multiple paths through the graph. So in this way, a single target provides supervision for many chains of contrastive learning problems in our graph. But of course, we still need to come up with this target. As we alluded to, we can turn our supervised learning problem into a self-supervised learning problem simply by turning our training sequences into palindromes, at training time only. And so this allows us to actually supervise all of these contrastive learning problems in our graph without any sort of human labels whatsoever. Now let's look at some visualizations of our model by looking at real data. So in the top row here, I'm showing an initial frame, and we're showing the query node in the white square. And so we can visualize the transitions to some future node. In other words, we're actually visualizing just an intention distribution on the future node. And we can see that our model actually works pretty well. The correspondence is actually quite exact. But what if we want to learn some sort of higher level correspondence, maybe at the level of the parts of an object or even the object itself? We can get at this idea of learning multiple scales of correspondence with an idea that we call edge dropout. In edge dropout, at training time, we simply randomly drop edges from the graph. This changes the nature of the task by forcing the model to consider alternate paths through the graph, to consider contextual paths through the graph, in a manner kind of reminiscent of the idea of common fate. And as we will see, this indeed does lead to improved higher level correspondence, for example, object-centric correspondence. In practice, as I said, we simply extract nodes by extracting a grid of patches from the image. And we map each of these patches to a representation using a ResNet encoder. We train the encoder on the kinetics dataset without any labels whatsoever. We evaluate the representation by using it as a similarity metric for video label propagation tasks involving objects, semantic parts, and key points. In label propagation, we're essentially given the labels of the first frame of the video, and the task is to predict the rest of the labels for the rest of the frames. So we think that these tasks require a representation that is in some sense robust to the natural transformations and dynamics of natural scenes. Concretely, we use a simple inference algorithm for label propagation based on nearest neighbors. And this also follows prior work. So we have a set of labeled nodes with corresponding categorical label distributions and a set of unlabeled nodes. And for each unlabeled node, we simply retrieve the top k most similar nodes and compute a linear combination of their labels based on the transition probability. So we essentially consider the top k transition matrix and use that as an attention matrix. Now let's look at some qualitative results of object propagation on the Davis task. On the left here, I'm showing UVC, which is a state-of-the-art method based on colorization. We can see that our approach is actually much better at respecting the boundaries of objects, even though there's this partial occlusion here. Here's another example that involves a lot more camera rotation, as well as a lot more object deformation and movement. Again, we can see that our approach is better at actually discriminating between the parts of the scene and segmenting the scene, as well as actually being more robust under the transformation of the viewpoint of the object. Quantitatively, we find that despite its relative simplicity, our model outperforms existing self-supervised approaches, including state-of-the-art approaches based on colorization, as well as approaches that use higher resolution feature maps. Our approach also outperforms strong image-level representation baselines, including networks trained on ImageNet with strong supervision, or methods trained with MoCo, which is a state-of-the-art self-supervised contrastive learning approach. Indeed, we find that edge dropout leads to improved performance on object-centric correspondence. And when we visualize features that are actually learned with edge dropout, we can see that they're more smooth within segments of objects. Because our approach is self-supervised, we can also use self-supervision at test time to adapt the model before evaluating it on each test example. And we find that this also leads to further improvements. Finally, we also find that our approach indeed also outperforms existing self-supervised approaches on the tasks of key points propagation and semantic parts propagation, despite never being trained for dense similarity, unlike techniques that are based on colorization. Overall, we've proposed a simple end-to-end approach for learning representations of correspondence from unlabeled video. The main idea is to learn a representation by learning to walk on a space-time graph constructed from video. A formulation allows us to supervise entire chains of contrastive learning problems in our graph by specifying a single self-supervised target. We hope that our work is a step towards scaling object-centric representation learning. Thank you.